In previous videos, we saw how logic gates combined with registers can be used to perform operations whose results can then be stored and modified. Imagine being a programmer who wants to give an instruction to the computer to perform an operation. Say you want to add 1 plus 1. Communicating this instruction entirely in terms of logic would be highly tedious and time consuming. Instead, we try to express our programs in a way that's easier for humans to understand. Just like how people use language to communicate, ISA is a medium of communication between hardware and software. ISA can be thought of as a guidebook to the language used by the programmer to communicate with the processor. Formally, the instruction set architecture, or ISA, is the part of the processor that is visible to the programmer or compiler writer. ISA defines all of the programmer visible components and operations of the computer. ISA provides all information needed for someone who wants to write a program in machine language or translate from a high-level language to machine language. Imagine you write a guidebook for a person to communicate in English. It will define words, different types of words, how to string words together, how to structure words into different types such as statements, questions, etc. Similarly, an ISA is a well-defined hardware and software interface. It provides functional definition of operations, modes, locations supported by hardware, precise description of how to invoke and access them. The ISA of a processor generally describes operand storage in the CPU, number of explicitly named operands, operand location, operations, and type and size of operands. The three most common types of ISAs, grouped according to how they store their operands, are stack, accumulator, and general purpose register. A stack is a basic data structure that can be logically thought of as a linear structure represented by a pile of plates. We can only access the plate at the top of the pile. That is, only the data at the top of the stack can be accessed. In stack, the operands are implicitly on top of the stack. Because the operands used in the instructions are always in a known location, that is, the top of the stack, the instructions themselves do not require memory addresses or register numbers to specify their operands. This leads to an instruction set architecture, or ISA style, known as a zero address format. For example, to perform C is equal to A plus B in stack architecture, we give the following instructions. Push A. This pushes A into the stack. Push B. A is moved into the bottom and B is on the top of the stack. Add. B is popped, then A is popped. Both are added and pushed back into the stack. Pop C. C is the result of the addition of A and B. The main disadvantage of the stack is that it cannot be randomly accessed. As you could see in the example, to access the third element from the top of the stack, one needs to take out the first and second elements from the top before accessing the third one. The stack itself is accessed in every operation and this becomes a bottleneck. To understand the next two models better, we will look at a side-by-side comparison of them. An accumulator-based architecture is an architecture that only has one general-purpose register, that is, the accumulator. It is an implicit single-element storage model. A GPR-based CPU architecture is a register-based architecture, has one or more general-purpose registers. In an accumulator architecture, most instructions operate on a single register called the accumulator. In GPR architecture, instructions operate on multiple general-purpose registers. Since there is only one register, that is the accumulator in the accumulator model, most operations have the accumulator as an implicit argument to the instruction. This means you don't have to specify where the operands go because there's only a single register, the accumulator, where it can go. For example, to perform C is equal to A plus B,
on an accumulator-based machine, the instruction sequence will roughly look like this. Load A. This loads the memory address of A into the accumulator. Add B. B is added to the existing value of the accumulator. Store C. The value of the accumulator is now stored in C. In contrast, in a GPI model, since there are multiple registers, the registers are explicitly specified in the instructions. Example: to perform the operation C is equal to A plus B, load R1, A. Data from location A is being loaded into R1. Add R1, B. Data from location B is being added to R1. Store C, R1. Data from R1 is being stored in the memory location of C. In the accumulator model, the operands need not be specified, leading to smaller instructions. In GPI model, all operands must be specified, leading to larger instructions. In accumulator model, most of the instructions depend on the results of the previous instruction. Therefore, CPU can often not do multiple instructions in parallel. In GPI model, it's easier for the CPU to do more independent instructions in parallel. In accumulator, the accumulator is only a temporary storage, so memory traffic is very high for this type of architecture. Earlier, CPUs were of the first two types, but in the last few decades, all CPUs are made of GPR processors. The two major reasons for this are that GPR registers are faster than memory. The more data that can be kept internally in the CPU, the faster the program will run. The other reason is that registers are easier for a compiler to use. 8086 ISA is an example of a widely used general-purpose register architecture. It is a combination of stack, accumulator, and GPR and can be used in different ways. Here is a sample diagram of 8086 ISA from electronicsdesk.com. Most ISAs allow you to work with the CPU as well as its components using simple instructions. Each instruction will contain an opcode. The rest of the instruction contains operands and information about the addressing mode. The three prime factors that make a good ISA are programmability, implementability, and compatibility. Programmability. Programmability can be defined as how easy it is for a compiler or a human to express programs. Compilers are good at breaking complex structures into simpler ones, but are not good at combining simple instructions to complex ones. Therefore, architecture with higher complexity are more programmable. Implementability. Certain ISA features such as variable instruction lengths and formats, implicit state, variable latencies, difficult to interrupt instructions, make the program less efficient to be implemented. Compatibility. Backward compatibility, the ability of new processors to support old programs, is very important. There is resistance to buy new hardware if it requires new software. The x86 still remains as one of the most commonly used ISAs because of its high compatibility. ISA can also be classified into RISC and CISC. RISC, Reduced Instruction Set Architecture. CISC, Complex Instruction Set Architecture. The main idea behind RISC is to make hardware simpler by using an instruction set composed of a few basic steps for loading, evaluating, and storing operations. This means that a load command will load data, store command will store data. CISC. The primary goal of CISC is to complete a task in as few lines of assembly code as possible. This can be achieved by building processor hardware that is capable of understanding and executing a series of operations. A single instruction will do all the loading, evaluating, and storing operations, such that a multiplication command will do stuff like loading data, evaluating, and storing it. Hence, it's complex. Both approaches try to increase the CPU performance. RISD does this by reducing the cycles per instruction at the cost of number of instructions per program. CISC does this by attempting to minimize the number of instructions per program, but at the cost of increase in number of cycles per instruction.
Earlier, when programming was done using assembly languages, lesser number of instructions were preferred because assembly language programming is tedious and error prone, due to which CISC architecture evolved. But due to the uprise of dependency on higher level languages, dependency on assembly reduced, and so RISC prevailed.